let us get started. We will continue with wherever we left off in the last class. All right. So there seems to be a good bit of lag between what I am showing and what you are seeing. Just one second. All right. So in the last class, I had started talking about different materials which we use in engineering applications. So broadly speaking, I had said that you have three classes of materials which you use: polymers, metals, and ceramics. Now, metals are used uh, wherever you have a requirement of stiffness and toughness. Okay, so the word, what does the word stiffness signify? What does the word stiffness signify? So stiffness signifies the quality of the material which relates to the deflections that it would undergo when it is subjected to a external loading. So like whenever, so some examples, so if you are taking for example a civil construction, or let us say a automobile chassis, or the frame of a CNC machine. Okay, so if you take these examples, in these examples, you want their shape to remain intact despite the external forces that are acting on the member. Okay, so whenever you want something to be rigid and you want it to not fracture in applications, you go with metals. Now, in metals, I had initially talked about the different alloys which are available, and the most widely used alloys happen to be, so steel is by far the most widely used metal, and then you have aluminum, copper, titanium, nickel. Okay, so alloys out of these different materials, and then in many alloy compositions you use chromium, nickel, molybdenum, zinc to some extent. Now, initially, I had talked about metal alloys in a general fashion as to when what is used. Now, let us look at a few specific alloys which are uh, which are very popular, and popular for a reason. It is always good to remember at least a few names with regards to metals. So the first material that we are going to talk about is AISI 4360. Okay, so this AISI is American Institute of Steel and Iron, and this number 4340, it basically it signifies the a certain class of alloys. Now here you have been given the composition of the alloy. Now, as you can see from the composition, you have chromium, nickel, molybdenum, manganese, silicon in small amounts, and the 4000 series alloys are very popular for their properties. So, whenever you are dealing with a steel alloy, you can use it in different states. Now, what is the state of the material which you get when you procure it from the market? So let us say you buy from a dealer a bar of 4340 alloy. What is the most likely state, or what is the state in which you would get the material? What are the different conditions in which you can get materials? So one of the conditions is the annealed condition. Okay, so most likely you are going to get the material in annealed condition. What is annealed condition? What is annealed condition? Aditya, Yashashvi, you want to answer? Yeah, Yashashvi, you can answer.
So I was saying that we were all muted. So like,
Uh, okay, how do I change that? Just give me a minute. Huh, fine. You can unmute yourself. Yeah. So, what is annealed condition? When you manufacture, let us say, material in the form of bar stock or plates, what is the manufacturing process which is used to manufacture either bar stock or plates?
So we heat it and cool it. Repeated heating and cooling is done.
What are you saying? What is the manufacturing process which is used for?
cold working.
Sheet forming.
You don't use cold
Rolling.
working, Baba. You normally use hot rolling. Okay. Now in hot rolling, what is the most common way in which the material is cooled to room temperature?
Quenching.
You don't do quenching. Quenching will make the material hard and brittle. Okay, so you typically let it air cool to room temperature. So whenever you take a material to above austenizing temperature and you let it air cool to room temperature, you refer to that particular condition of the material as annealed condition. Now, what is the advantage of having a material in annealed condition? What is the
It is very
Higher,
advantage?
ductile.
Sorry,
It
higher
is very
ductility.
ductile.
the material is ductile, and anything else? What can you say about its, let's say, yield and ultimate tensile strength vis-a-vis a material which has been quenched and heat treated?
Oh,
What
no,
will
sir.
be the
Yes.
what will be the yield and ultimate tensile strength of a material in annealed condition as compared to that in quenched and tempered condition?
So it will be lower.
It will be lower. Very good. So now, why do you think you would want your raw material to be in a softer state when you procure it directly from a vendor?
So the
So
machinability is better.
Yeah, so see, after you procure the material, you have to carry out a lot of processing on it. You may have to do some forming operation, and then you may have to do machining, grinding. You have to do a lot of operations on it. Now, whenever you are either forming it or you are machining it, do you want it to be really hard, or do you want it to be means softer?
So softer would be better.
So whenever you are processing the material, you want the material to be softer. and only in the very end stage you are going to subject it to a heat treatment process and then finally carry out something like grinding operation in order to get the precise dimensions that you want. So the material is normally available in the annealed condition. Now for this particular alloy, even in annealed condition, it has a yield strength of 470 megapascals and it has a tensile strength of 745 megapascals. So in comparison to low carbon steel, what is the percentage by which the yield strength is higher for 4340 even in annealed condition? So if you take low carbon steel, see there are some numbers which you have to remember. You can always go to Google and get some numbers, but you should always remember certain things. So low carbon steel is a widely used material, so you should know its properties. So low carbon steel has a yield strength of around 230 megapascals and it has a ultimate tensile strength of around 350 megapascals. So if I take mild steel, okay, so it has yield strength of around 230 megapascals and UTS of around 350 megapascals. Okay, so in comparison to that, you see even in annealed condition AISI 4340 has strength which is a little which is about double of that of mild steel. And one more interesting point that you can note is that if you look at the Young's modulus or elastic modulus of the material, it doesn't really change from alloy to alloy. So the Young's modulus is always around 200 GPa. So the stiffness of a steel alloy is nearly independent of its alloy composition. There is a variation of about 5%, but there is a huge difference in the yield strength and ultimate tensile strength as you go from alloy to alloy and as you go from one heat treatment condition to another. The most common heat treatment conditions you will find is annealed or normalized condition. Normalized means you cool it in a furnace. Annealed means you cool it under ambient conditions in the outer atmosphere. So you find it, most common condition you find a material in is annealed condition. And then you have quenching and heat treatment. So whenever you want your part to be really hard, okay, so why would you want your material to be very hard? So take for example, so sorry, let me go back to the previous slide. So what are the parts which I am showing over here? Like what is this part here?
So camshaft.
So this is cam. What is this?
That's a crankshaft.
That's the crankshaft. What is this? What is
It's a
this?
gear of some kind.
It is a gear. Okay, it is a helical gear. Okay. Now, uh, I have pasted these pictures. What is special about these applications? Let's start with gears and camshafts. Okay. So, uh, what do you think happens in these applications? Means I specifically chose these applications to highlight the use of this material.
Sir, there is a lot of rubbing involved.
There is good amount of sliding or rubbing which is involved. Very good. So what is the failure mechanism you would be worried about?
Sir, where, I guess.
Wear
Wear.
and tear.
Very good. So wear and tear is a very means that is something we are really worried about. And what would happen if the hardness of the material is low? It would wear out quicker. Okay, so to have long life we would need the material to be hard. So that is one issue. do you perceive any other issue? So whenever you have contact between two bodies, because steel is a very stiff material, what can you say about the area of contact, let's say between a roller and a camshaft, or between two gear teeth? What do you think would be the nature of area of contact?
So it would be a
If
line
it was
contact.
perfectly rigid, what would be the area of contact?
So perfectly rigid would be line contact.
No, I mean
Line, it will be like a
area
line.
of contact. It would be a line or a point. So what will be the area of contact? What is the area of a line?
It
What
will
is
be
the area of a
very
point?
negligible.
Negligible.
Zero.
Okay, it would be zero. If it is rigid, it would be zero. Okay. Now these are not rigid, but they are very close to rigid. Okay, the stiffness of these materials is very high. So what do you think will be the nature of area of contact? Will
Very
it
low.
be, it would be very low. Okay, many of the contact, yeah, the contact size will be very small. So now, but on the other hand, what will be the kind of forces which will be transferred? So if you are talking about a gear system, okay, so you would be transferring quite large forces but across very small areas. So what will happen to the contact stresses? The
Stresses will be
contact
very, very
stresses will
large.
be
Very
very
high.
large. Okay, so in applications like camshafts and gear teeth, you have rubbing, you have sliding, and you also have very large contact stresses. Now very large contact stresses, what kind of a failure can they induce?
So fracture.
Fracture.
No, Baba, it won't fracture immediately. It will result in something called rolling
So
contact fatigue. Okay. So, if you are not speaking, please put your microphone on mute. I'm hearing some background noises. So, when you answer, you please unmute. Otherwise, you put your microphone on mute.
Sir, you can mute him. I guess he's forgot.
So you also went on mute, I guess.
Yeah, so if there is an impact like situation, then it can also result in indentation. So for all these reasons, in applications like camshafts, gears, bearings, you require the material to be very hard. So in order to increase the hardness of the material, we subject it to heat treatment process. We use the word heat treatment because it's not a single thing that we do, but we subject it to a process. What are all the steps which are normally involved in a heat treatment process for a steel alloy? What are the typical steps which are involved in heat treatment process for a steel alloy?
Sir, heating and then quenching, I guess.
So you first do furnace heating, and you, to what temperature do you heat it?
above the austenite.
Above the
So
austenizing
you take it
temperature.
above the austenizing temperature, you keep it above the austenizing temperature for some time. What is the purpose of taking it above the austenizing temperature and then keeping it at the temperature for a while? What is the purpose?
So to allow diffusion.
So that you end up with a solid solution of your alloying elements. What you want to do, it is something like this, that you have, if you add sugar to water, lot of sugar to water at room temperature, it may not dissolve properly. Sugar is accumulated at one place. So what do? You raise the temperature of water. So that will basically have the sugar dissolve in water, and sugar molecules are basically spread out across water. In the same manner, if you take the material to above austenizing temperature, all the alloying elements basically uniformly disperse within the material. And then what do you do after that?
We can do annealing or
Quenching.
quenching.
We can do annealing or quenching. So if you want to increase the strength of the material, then what do?
We quench it.
You quench it. Okay, normally you subject it to an oil quenching process. And then do we directly use the material after the quenching process?
No,
No,
sir.
tempering is done.
Yes, sir.
No, we do not use it immediately after the quenching process. The material is hard, but it is also brittle. And there are also a lot of residual stresses present within the material. So what do you do afterwards?
Tempering.
You do tempering. So what is tempering? You place the object in some sort of a oven. Okay, we or again another sort of a furnace, but now you do not take the temperature to above austenizing, but rather many a times you take it to somewhere around 100 degrees Celsius, place it at the temperature for a couple of hours to relieve the stresses, and also to basically change the microstructure in a manner that the material becomes tougher, means its ductility improves. So let us see, like for 4340 steel, what is the effect of this heat treatment process. Now, what you are looking at in this table, what is given is you are given properties of the material after 48 hours of tempering. Okay, so basically it is being tempered for 2 days. Normally, you do not temper for so much time. Tempering is typically done for about 2 hours. So, anyhow, effect of 2 hours versus doing tempering for 48 hours is given in the graph below. But in the table, the results shown are for 48 hours of tempering. And you can see what is the effect of tempering at different temperatures. So over here, tempering temperature are being varied from 100 to 650, and properties are also given for quenching condition. Okay. So what do you observe? So the first property that is being talked about is the yield strength of the material. Now the yield strength of the material when you quench it is 215 megapascals, or close to 2 GPa. That is high value of yield strength. And if you heat treat it, if you temper it, you can see that at 100 degrees the yield strength reduces to about 1.8 GPa. At 200 degrees of tempering, it reduces to 1.55 GPa, and so on. So as you increase the tempering temperature, it keeps getting softer and softer. But if you look at ductility, there is not much difference in the ductility actually. So percentage elongation is roughly 10%, okay, for a wide variety of tempering temperatures. So you don't get much benefit. Okay, hardness is reducing considerably, but ductility is not increasing much. That is the reason that tempering is typically done at about 150 degrees or 150 degrees Celsius. And the effect of tempering time is shown in the graph below. And you can see that if I look at this 100 degrees tempering temperature, you can see that between the so if I'm looking at yield strength, which is basically the dashed line, you can see that there is very little difference in the yield strength. So triangle is for 2 hours, circle marker is for 48 hours. You can see there is very little difference. For 2 hours it's slightly harder than before, but in terms of ductility, once again, if I look at this, so if I look at percentage elongation, so for 100 degrees, something is not right. For 100 degrees, for 2 hours tempering, it is about 9%, and for 48 hours, it is about 10%. Okay, there is very little difference in the increase in ductility if you temper it for 48 hours. This is the reason that most of the times tempering is done for about 2 hours. So what are the main points to be noted over here? So 4000 series alloy, specifically 4140 and 4340 alloys are used for making shafts, cams, crankshafts, gears. So in all applications where the stress which material would be subjected to would be very high, and it can also be subjected to some amount of impact loading, there we go with this particular alloy. Machining is done when the material is in annealed condition, but for the final part, after machining is completed, you subject it to quenching and tempering conditions. Tempering usually done at about 100-150 degrees for about 2 hours in order to increase the hardness of the material and get reasonable amount of ductility within the material. So for this 100-150 degrees of tempering, the yield strength that you get is close to 1.8 GPa. So what is the percentage increase in yield strength in comparison to mild steel? So if you look at quenched and tempered 4340 steel, what is the percentage increase for 4340 as compared to mild steel? Do it and tell me. 1800 divided by 230, how much is it? How much is it? You can hear me?
7.826.
7.826. So that is close to 800% higher. Okay, so the yield strength is about 8 times higher as compared to that for the low carbon steel. Now, another variety of steel which is used whenever you require very high hardness is AISI 52100. There is a lot of lag. I am unable to. Okay, 52100 steel. Now, over here, um, so 52100 steel, uh, this contains, this is a high carbon variety of steel. You can see that the carbon percentage is close to 1% over here. You also have a little bit of chromium in here. All right. And this particular variety of steel, um, this particular variety of steel, you can see has got very high strength. So the properties shown over here is after you do quenching and tempering at 150 degrees Celsius for 1 hour, and you can see that the tensile strength of the material is very high. So at room temperature, it is not shown here, but you can see for 200 degrees Celsius, it is close to 2.5 GPa. All right. But as opposed to 4340, you see that but you see that the tensile strain or the fracture strain of the material is very small. At room temperature, the material fractures at 1% strain. So what does it mean? Practically speaking, what does it mean?
It can sustain very little deformation.
Very
Very
little
brittle.
deformation. So what do we call such sort of materials?
It's very brittle.
Brittle.
Stiff.
Material is very brittle. So one practical implication is when you are handling bearings, if you accidentally drop a bearing, there is a very high likelihood that the bearing will fracture. Okay, similar to a glass item or a ceramic, a porcelain item. If you drop a porcelain or a glass item, it's going to break for sure. For bearings, there is a high probability that it may happen. And also what this means is that if you take a hammer and you are going to hit against a bearing, once again there is a high likelihood that you may end up fracturing a bearing. So this particular variety of material is used for bearings because of its very high hardness, but it is brittle and after the heat treatment, and you have to be careful when you are handling bearings. Now next, moving on to the stainless steel varieties. So I have covered two alloy compositions, one which has high hardness and high toughness, and one which has very high hardness but is not that very tough, which is brittle. Next, moving on, another class of steels which are very popular are stainless steels. So what does this adjective stainless refer to?
Resistance to corrosion.
These steels have high resistance to corrosion. And so basically, how is the corrosion resistance achieved?
By alloying it with chromium.
So these steels have high chromium and nickel percentages. So if you look at SS304, so 304 has got minimum 18% chromium and it has about a minimum of 8% of nickel. Okay, so the high chromium and nickel percentages give it the basically the chromium oxide coating gives it the corrosion resistance, and mm, these high alloying basically transforms the microstructure from ferrite to austenite. So SS304 is austenite, means it's an austenite grade of steel. What is the means what is one property which changes as you go from this ferrite to austenite structure? So SS304 is basically non-magnetic. Okay. So if you want to know if something is actually a pure stainless steel or if somebody has just given a nickel plating, you can take a magnet to the means let's say the cutlery item or something else that you're looking at. If it sticks to it, then it means it's actually not pure stainless steel. Maybe it is just nickel plated or it is some other grade of steel, but it is not the 304 grade. So 304 has got good corrosion resistance, and amongst the stainless steels, it is the most widely used one. Now, whenever you're looking at the stainless steel grades, you will see like two extensions to the name. So you can see that there is a 304 variety and there is a 304L variety. What does this L signify? L signifies basically low carbon percentage. Okay. So normal carbon percentage is 0.08% in 304, but in 304L it is 0.03. Why do you care about the carbon percentage? Why do you care about the carbon percentage?
It controls the hardness of the steel,
Not so much.
perhaps the ductility.
More carbon makes it brittle.
No, no, no. Stainless steels are very tough and they have very good ductility. You can form them really well. Carbon percentage becomes important when you are welding stainless steel components. Okay. So when you are welding, what happens is chromium reacts with carbon to form chromium carbide, thereby depleting chromium in the neighborhood of the weld. And the joints become susceptible to corrosion. If you use low carbon percentage, you reduce this chromium depletion within the means around the weld zone. So it is for this reason that carbon percentage is very important in stainless steels. Now another grade of stainless steel which is also very popular is this SS316. Okay. Now 316 variety, a new thing which gets added is the molybdenum content. You anyhow have your chromium and your nickel. Okay, nickel is in fact a little higher in 316 as compared to 304. But in addition to this, you have molybdenum being added, and because of the addition of this molybdenum and higher percentage of nickel, what you get is a greater corrosion resistance, okay, particularly against the chlorides and industrial solvents. And also because of this molybdenum, you also have a higher high temperature strength and creep resistance. So 316 is used, for example, in medical instruments, food processing, okay, when you are handling salt water, for example, in some reverse osmosis water filtration systems, and also they are used in nuclear plants, places where you will have to deal with high temperatures. You want and you are having highly corrosive environments, cost is less of a concern. Then in those conditions we go with 316. Once again in 316 you have a L and you have a N. So when you have a 316L, automatically carbon percentage is small, so you can see 0.02 to 0.03 percentage. And N, nitrogen, you are increasing it, you are wantedly adding it. Why do you think we are adding nitrogen? So you can see from this graph over here that as the nitrogen increases, what is happening? You have an increase in the yield strength of the material. So this is the reason that nitrogen is being added. So if cost is not a concern, then you would go with something like 316LN variety of stainless steel. Okay. All right. So that covers the stainless steel varieties. Now moving on to the ceramics. Uh, so amongst the engineering ceramics, we use alumina, silicon carbide, tungsten carbide, uh, yttria stabilized zirconia, and something else. Now alumina is by far the most widely used ceramic. Okay. Now what is the most common reason why something is most widely used?
It's cheaper.
Cheap.
Because it has decent
Cost
set of
effective.
properties and it is cheap. Okay, so alumina happens to be like the cheapest of the ceramics. As you can see, I have put the cost over here. It costs about 50 rupees per kg, and it also has a relatively low density. Okay, so it happens to be the most widely used ceramic. Now one very interesting property of ceramics is that they have a much higher strength in compression in comparison to the strength in tension. Okay, so if you compare the tensile strength to compressive strength, this and this, you can see that the compressive strength is 12 times that of the tensile strength of the ceramic. By the way, all this strength is after you have densified the ceramic to form a component, not in the form of powder. Of course, powder has no strength. And the most common method that you use to make the ceramics is through the sintering process. So you start with powder, that is the form in which you get the material, and then you put it in some dye and you subject it to pressure and elevated temperature in order to form the part. One of the things about ceramics is that their melting temperatures are all quite high. Okay, so melting temperature of ceramics are typically above 2000 degrees Celsius. So alumina melting temperature is 2072 degrees Celsius. Okay, and after you sinter it and you have formed more or less a fully dense ceramic, their thermal conductivities are actually quite decent. So in the case of alumina, it has a thermal conductivity of around 30 watt per meter Kelvin. So what is the thermal conductivity of stainless steel? Do you remember? What is the thermal conductivity of stainless steel? All of you have access to Google now. So even if you don't remember, you can tell me the answer nonetheless.
15, sir.
So it is 15. So you would think that ceramics would have low thermal conductivity because of some perceived notion, but actually their thermal conductivity is per se not low. So for alumina, it is in fact twice the thermal conductivity of stainless steel. It is lower than many other metals, but it is comparable. So all right, I'll continue more in the next class. I'll just share a form and you fill it up based on whatever you have learned today. Yes, give me a minute. All right, I have pasted the form. Please, yeah, try to finish it up before 11 o'clock. If you have any questions, you can ask. If you want to talk about something, you can do that.
Sir,
Yeah,
sir, will you be uploading the slides in the Teams?
I have already done. One second, let me check. For this material selection, I have done this, I guess. Let me check once.
So, so, so why this centering process is used? You were talking about the centering process.
So, mm see, what can you say about the melting temperature of ceramics in comparison to that for metals or plastics?
So it's very high. It's
It
higher
is
than the.
very high. So, what is the means? So, like melting a material and casting it into a mold is not really an option for ceramics. Their melting temperatures are so high that means it makes more sense to start with material in the powder form and then you subject it to like pressure and elevated temperature. You take it close to their melting, but you do not really cross their melting temperature. Okay, so at this elevated temperatures you basically subject them to pressure, and that will lead to densification of the powder in order to get the final part.